Have you ever wanted to play the role of a scientific detective? Well, today we're investigating exactly how we can actually see the submicroscopic world of chemistry. We're talking about the fundamental transformations that literally govern our universe, chemical reactions. So, let's dive into this massive question. How do we witness the invisible? Atoms are far too small to see, yet their microscopic collisions build and destroy our entire reality. We obviously can't watch the individual bonds break, but we absolutely can look for the macroscopic aftermath of these tiny invisible events. You see, a chemical reaction is essentially a profound atomic reorganization. It's a process where reactants break their chemical bonds and shuffle their atoms around to yield entirely new substances with completely distinct chemical and physical properties. It's like a giant puzzle rearranging itself. And when these bonds break and reform, they leave behind evidence at the crime scene, evidence we can observe right out in the open with our naked eyes. Here on our clue board are the 5 unmistakable characteristics of a chemical reaction. Think of these as the macroscopic fingerprints of chemical change. We're looking for a change in state, a change in color, the evolution of gas, a change in temperature, and the formation of a precipitate. Let's investigate each one to understand exactly how this chemical language works. Our very first clue is a change in state, but we have to carefully distinguish this from a mere physical change. For instance, melting ice is just water changing its shape, right? It's still water. But burning solid paraffin wax, that is a true, permanent chemical reorganization. When you burn a candle, that solid wax doesn't just melt away into nothingness. It chemically reacts with oxygen, completely transforming into gaseous carbon dioxide and liquid water vapor. It's a massive permanent change in state, and it gives us absolute empirical proof that a chemical reaction has actually occurred. Clue number 2, a change in color. Shifts in atomic structure can completely alter how a substance absorbs light. A classic example of this is a simple displacement reaction. If you take a standard iron nail and drop it into a deep blue solution of copper sulfate, the more electropositive iron literally kicks out or displaces the copper. The result? The liquid fades to a pale green iron sulfate, while simultaneously coating the nail in solid brown copper metal. That color change tells the whole story of the electron transfer. Another totally dramatic shift happens during the reduction of bright orange dichromate into a stark green chromium ion. When atoms trade electrons, they completely alter how they absorb light, painting our world in totally new, distinct colors. So whenever you see these sudden shifts in optical absorption, you know for sure that the atomic bonds are being heavily reorganized. Moving right along to clue number 3, the evolution of gas. Dropping electropositive zinc into sulfuric acid rapidly displaces the hydrogen, generating these highly volatile gas bubbles that violently escape the liquid. And you know what the fun part is? You can actually catch that invisible gas and test it with a burning match. If it ignites with a high-pitched squeaky pop, you've just proved the creation of hydrogen gas. That tiny pop sound is undeniable, real-time proof of a chemical reaction. Clue number 4 brings us to a change in temperature. Because breaking and forming atomic bonds inherently requires and releases energy, chemical reactions often create massive temperature shifts that we can easily measure or even just feel. When some chemicals mix, they experience a huge spike in reaction enthalpy, releasing immense amounts of heat into their surroundings. We call these exothermic reactions, and they are honestly some of the most dramatic chemical events you can witness. A perfect example of this is mixing quicklime with water to create slake's lime. This specific combination generates so much heat that if you were to touch the container, it could easily burn you. That intense, radiating heat is direct, visceral evidence of new, much more stable bonds forming. And finally, clue number 5, the formation of a precipitate. This is perhaps one of the most visually stunning indicators of a reaction. Swapping ions in aqueous solutions through a double displacement reaction can synthesize an insoluble ionic lattice. Because this new structure absolutely cannot remain dissolved, it literally falls out of the clear liquid as a brand new solid, seemingly out of thin air. Take, for example, mixing 2 clear liquids to get an instantaneous white barium sulfate or a brilliant yellow lead iodide. Let's isolate that second example for a second. You mix two completely clear liquids, lead nitrate and potassium iodide, and instantly conjure this opaque yellow paint-like substance. It's almost like magic, but it is undeniable, absolute proof that the atomic bonds have completely rearranged themselves. The final verdict? The law of the universe. Now that we've gathered all our macroscopic clues, change in state, color, gas evolution, heat transfer, and precipitates, we must look at the ultimate rule governing them all. No matter how dramatic the color change or how violent the gas evolution is, Antoine Lavoisier's foundational law of conservation of mass applies. It dictates that mass can neither be created nor destroyed in a chemical reaction. Every single atom from the reactants is perfectly accounted for in the products. They haven't vanished, they are merely wearing new molecular masks. And this brilliantly illustrates the most profound takeaway of all. Since every single atom in our own bodies obeys this exact same chemical accounting system, it leaves us with a truly fascinating question about the eternal recycling of our universe. If mass is never lost in any chemical reaction, where do you go when you're gone?